Hello, and welcome to our next example in optimization from section 4.7 of our calculus textbook. So I'll read along with the problem here just to get a sense of what it is that we're trying to do. And remember, we're going to try to follow the outline that I've provided you. We have a rectangular box. It's got a square base, but no top. And it's going to be constructed out of two materials. We probably want the bottom to be stronger than the sides, and so the bottom is going to be a more expensive material. It's going to cost $4 per square foot, and the material for the sides are only going to be $2.50 per square foot. And we want this box to have a volume of 24 cubic feet. And so the question before us is, how long should I make the length, width, and height of the box in order to minimize how much it costs me to do so? And we're going to assume that cost here is only materials. We're not going to account for labor. And so we may want to start by looking at our question here. What dimensions are going to minimize the cost of constructing the box? And so when I see the word minimize and what I am trying to minimize, that tells me what it is I'm going to optimize in this case. And so my goal is going to be minimize the cost, and I'm going to give it a letter name, C, of construction. So generally speaking, especially when these problems are geometric in nature, a sketch is probably a good thing to have on hand. So here's my attempt at drawing this box. So we want to at least have a bit of a sense of what it is that we're looking at, and we'll need to think about some geometric formulas that are related to various aspects of the box. And so if I read carefully, I see two things I have to account for when I'm going to construct some equations below. And so I want to think about the square base. And so the square base tells me that length is going to be equal to width. So if I'm trying to come up with my other variables, I don't need to have a separate variable for length and width. I'm just going to call them both x. And I can put them here on my diagram. And then the other thing I need to account for is the height of the box. And so we're taking advantage of reading carefully and recognizing that we only have two other variables. We don't need to have separate variable names for length and width. And so the next thing we need our objective equation. That's the equation that involves the quantity that we're trying to optimize. And so our goal here is to express cost in terms of x and h. And so if I want to think about how am I going to figure out how much the materials for this box are going to cost, well, I want to note here that the total cost is going to be the sum of the costs of the faces of the box. And so I want to recognize that there are 5 faces that we have to deal with, and this is where the no top comes from. Ordinarily, we think of 6 faces being in a rectangular box, but here we have only 5. So let's note what those are. There's this face. We have some lateral faces, 4 of them, and then we've got a bottom as well. So I've got the bottom here. So I've got 5 faces, and so I need to compute the cost of each of these 5 faces. So let's look at the bottom first. And so let's try to think about how I would construct the cost of the bottom. Well, if it costs $4 per square foot, suppose I told you that the area, the surface area of the bottom was 7 square feet. So if it cost me $4 per square foot and I had 7 square feet, that would be 4 times 7, or $28 that would cost. And so apparently I'm going to multiply the cost per unit area times the area. So here's a big piece of this here. So the cost of a face is going to be the cost per unit area times the area. So the cost of the bottom then, that's going to cost $4 per square foot. And how many square feet do I have? I'm not dividing. Well, the area of the bottom is, I've got a square bottom, and so I just know that the area of a square is the side length squared. And so I've got, so let me go back and change this. This is $4 per square foot. That's where my division should have been. And then I've got x squared square feet. So those cancel, and that leaves me with 4x squared dollars. Then I can think about do the same thing. The cost of a lateral face is going to be $2.50 per square foot. And now let's think about what the area of a single face is. Well, I've got h as my height, and I've got x as my bottom. And so in terms of length times width, that's x times h. That's going to be in square feet. So again, square feet are going to cancel, and I get 2.5 xh dollars. But there are 4 of those, and so I'm going to multiply this figure by 4. So the total cost is going to be the cost of the bottom, I'm going to leave off the dollar signs for right now, plus 4 times 250xh, or c equals 4x squared plus 10xh. And this is my objective equation. I'm expressing the cost in terms of my other variables. For my constraint, I haven't yet taken into account the volume, and so I'm constrained by how many cubic feet the volume is supposed to be. And so my constraint is volume equals 24 cubic feet, or x, so the volume is going to be x times h, x squared h equals 24. And so that's my constraint. So here's the objective, here's the constraint. So now let's remember what we do. We get the objective equation in terms of one variable. I'm going to solve the constraint for one of the variables and substitute it in. Okay, well, here if I've got x squared h equals 24, it's probably easiest to solve for h. And then what I'm going to do is I'm going to take this expression for h and put it in right there. And so I get c is equal to 4x squared plus 10x times 24 over x squared. And I can simplify that to 4x squared plus 240 over x, because we notice that this x is going to cancel with one of the x's right there. So here's what I want to work with. And then in terms of my domain, well, notice that as opposed to the previous problem, x can't be 0 because I would be dividing by 0 right there. But there's actually no upper bound on what x can be, because I could still have, I have to have 24 cubic feet as my volume. And so even if I had really, really long sides on the bottom, if x was really, really big, the height could be very, very tiny, and I could still get a box with 24 cubic feet in it. And so my domain is x bigger than or equal to 0. Now that I've got all that set up, I can use calculus. So what we're going to do here is we're going to find the critical number. So C prime is 8x minus 240x. So I want to solve C prime equals 0. 8x equals 240 over x squared. 8x cubed equals 240. X cubed is equal to 30. And so x must be the cube root of 30. And if we're looking at this, this is about 3.1 to 1 decimal place. So this is my critical point. But one thing that we want to be careful of is we always should verify that this is going to give us a minimum cost. And so I'm going to use the second derivative test because I don't have a finite interval like I did in the first example. I have to use this. I'm going to use the second derivative test to judge that it's a MAT, if it's a min occurring here. And so C double prime is going to be 8 plus 480 over x cubed. C double prime of the cube root of 30 is equal to 8 plus 480 over the cube root of 30 cubed. And I get 24, which is definitely a positive number. And so since C double prime is positive by the second derivative test, a min occurs when x is equal to the cube root of 30. But I should go back and determine what h is, because I was asking what the dimensions were. So I want to make sure I'm going to answer my question. What is h? Well, back up here, we said that h was 24 over x squared, and so I can determine what h is. H is going to be 24 divided by the cube root of 30 squared, and this turns out to be about 2.5 to 1 decimal place. And so to answer this problem in context, the dimensions of the box, which minimize cost of construction, are 3.1 inches by 3.1 inches by 2.5 inches. And this is length, width, and height.